Most physicists try to make sense of time. They comfort themselves with the idea that moments fade and suffering is washed away. But Dirac, legendary for his icy austerity and his insistence that the laws of nature must possess mathematical beauty, believed something almost unbearable. Time does not pass. His equations forced a reality where past and future are equally inescapable. But why did Dirac accept a universe so hostile to comfort, and what secret price do we pay for seeing it as he did? Paul Dirac was born in Bristol, England, in 1902. Even as a child, he spoke rarely, preferring the quiet order of mathematics to the noise of ordinary conversation. Family letters and his biographer Graham Farmelo describe a household ruled by strict discipline. Dirac's father, a schoolmaster, demanded that Paul speak only French at the dinner table, punishing him for mistakes with silence. This upbringing left marks that never faded. At Cambridge, Dirac's lectures were models of precision and brevity. Students recalled that he would pause for long stretches, refusing to fill the air with unnecessary words. His scientific papers were stripped of ornament, each sentence pared down to its essentials. Colleagues often found Dirac's emotional reserve unsettling. He would listen in meetings, immobile, then offer a single, perfectly chosen sentence. When asked about his motivations, he spoke of beauty, not comfort, not intuition, but the elegance of mathematics itself. He said, "If one is working from the point of view of getting beauty in one's equations, and if one has really a sound insight, one is on a sure line of progress." For Dirac, physical laws were not judged by how they made people feel, but by the symmetry and simplicity they revealed. He believed that the universe itself must be beautiful, even if that beauty was cold and indifferent to human hopes. This insistence on mathematical beauty was not a pose. It drove his work more than any desire for recognition or even understanding. In 1933, at just 31, Dirac was awarded the Nobel Prize in Physics, sharing the honor with Erwin Schrödinger for their discoveries in atomic theory. Yet Dirac accepted the prize with the same reserve that marked his daily life. He gave little attention to ceremony or fame, preferring the solitude of his study and the silent rigor of equations. To those around him, it seemed as if Dirac's world was made not of moments and memories, but of structures, abstract, eternal, and exact. Every page of his manuscript reflected this austerity, each line guided by the conviction that truth and beauty are inseparable in the language of nature. The Dirac equation stands apart from every other attempt to describe the electron. Instead of treating time as a special flowing background, Dirac placed it on equal footing with space. He began with the relativistic energy-momentum relation, E squared equals P squared C squared plus M squared C to the fourth. The challenge was to translate this into quantum mechanics, where energy and momentum become operators. The earlier Klein-Gordon equation, built directly from squaring both sides, led to mathematical problems, including negative probabilities, and no natural way to include the electron's spin. Dirac's solution was to linearize the equation. He searched for a form where energy and momentum would appear only to the first power, not squared. This required a new kind of mathematical object, the gamma matrices, labeled gamma mu with a Greek index. These are not ordinary numbers, but 4x4 matrices, each one corresponding to a direction in space-time, 3 for space and 1 for time. Their algebra is strict. The anti-commutator of any two gamma matrices equals twice the Minkowski metric, preserving Lorentz invariance. The equation can be spoken as I times gamma mu partial mu minus m times psi equals 0. The four gradient is partial mu where the time derivative appears as partial zero, that is, the derivative with respect to c times t. Time in this framework is simply the zeroth coordinate, no more privileged than x, y, or z. The unknown psi is not a simple wave function, but a four-component spinor. Each component encodes a different aspect of the electron's quantum behavior, including its intrinsic spin. The structure of the equation means that the laws of physics look the same to all observers moving at constant velocity, an essential demand of special relativity. In Dirac's formalism, there is no absolute now, no flowing instant. The entire evolution of the electron is written as a relationship between coordinates in space-time, stitched together by the gamma matrices and the spinor field. This treatment of time is not a philosophical statement, it is a mathematical consequence. The Dirac equation does not describe a process unfolding from past to future. It links all events through a single covariant structure, where time is just another axis in the geometry of nature. The groundwork is laid. The equation's symmetry and austerity reflect Dirac's own, but the mathematics soon uncovers something stranger, solutions that seem to run against the grain of physical intuition. In the summer of 1932, a thin glass plate inside a Caltech cloud chamber captured a single, unmistakable curve, a particle bending the wrong way. Carl Anderson, a young physicist working under Robert Millikan, had exposed the chamber to cosmic rays while searching for traces of high-energy particles. Most left familiar signatures, but this one track arced in the opposite direction from any known electron, its path marked by a sharp, bright line. Anderson measured the curvature, checked the magnetic field, and recalculated. The particle had the same mass as an electron, but carried a positive charge. He called it the positron. 4 years earlier, Dirac's equation had forced physicists to confront negative energy solutions, mathematical ghosts that at first made no physical sense. Dirac's answer was a bold hypothesis. What if all those negative states were filled, forming a vast invisible sea? A missing electron, a hole, would act as a particle with positive charge and positive energy, a mirror image of the electron, born not of experiment, but of mathematical necessity. Many doubted this idea, dismissing it as a trick or an embarrassment. Pauli called it the saddest chapter in modern physics. Yet Dirac insisted the symmetry was too beautiful to ignore. Anderson's photograph turned abstraction into reality. The positron was not a fantasy or a flaw, it was real, streaking through the chamber as a direct consequence of Dirac's formalism. Letters flew between Caltech and Cambridge, and the 1932 Physical Review paper made the connection explicit. Here was the antimatter Dirac's mathematics had demanded. The positron's discovery did more than solve a paradox. It proved that the equations, however austere, could reach beyond what anyone had imagined, uncovering a new kind of matter through the logic of symmetry alone. For Dirac, this was confirmation that beauty in mathematics was not a luxury, but a guide to the deepest truths of the universe. In the geometry of modern physics, time has no special status. The Dirac equation, like Einstein's relativity, is written in the language of four-dimensional space-time. Every event, each flicker of an electron, every heartbeat, every loss, sits at a fixed coordinate in a vast, unchanging manifold. The interval between events, described by the mathematical formula DES squared, equals minus C squared D T squared plus D X squared plus D Y squared plus D C squared, defines the structure of reality. There is no flow, no current sweeping one moment into the next. Instead, the universe is a block, its past and future equally real, each instant etched forever into the grid. This is the block universe. In this picture, the present is not privileged. The laws themselves, Lorentz invariance and the strict symmetry of the Dirac equation, demand that time and space be woven together, interchangeable under the right transformation. No observer, no matter how fast they move, can claim their now as universal. The mathematics is relentless. Every world line, every history, is a path through this frozen landscape, and nothing can erase the coordinates of suffering or joy. Dirac himself refused to speculate on what this meant. He spoke only of measurables, of what could be calculated or observed. When pressed about the nature of time, he offered silence or a technical answer, never comfort. Yet his equations have consequences that reach beyond physics. If the block universe is true, then the pain of the past is not lost. It remains fixed and inescapable. The future, too, is already written into the manifold, waiting to be discovered, not created. For many, this is an unbearable thought. For Dirac, it was simply the shape of truth, revealed by the symmetry and austerity he pursued all his life. Physics today still follows Dirac's lead, choosing truth over comfort, even when it unsettles us. The block universe remains our best scientific map of reality. As we measure time, we confront a cosmos that never forgets. The equations endure, even if our hearts resist their consequences.